Let's talk about work in physics. Uh, when we talk about work in physics, we're talking about transferring energy. So, in this example, the horse transferring some of its energy to the mass that it's dragging across the floor. So, think of it as converting chemical energy in the horse's muscles into heat, because when you drag things and there's friction, it generates heat. Now, there's a couple of key definitions we're going to keep coming back to. The idea of work being energy that's been transferred. So whenever you do work, you're transferring energy from one place to one thing to another. And work is defined to be the force that you apply multiplied by the distance you pull it through. And it has units, therefore, of Newton meters, newtons times meters, which is equivalent to 1 joule of energy. The other definitions we are going to use today are power, which is the rate that we transfer energy at, otherwise known as the rate of working, and that's measured in joules per second. So we can figure out how much work was done by the horse just now. It was 2.5 meters multiplied by 200 newtons, so we have 500 Newton meters of work, also known as 500 joules of energy transferred. Now, if we suppose that the horse took 5 seconds to do that, we can also tell you how much power it was outputting. Power is the work done divided by time taken, and so that is 500 Newton meters of work divided by 5 seconds. It's 100 watts, which seems a little low for for a horse. Now, the units of power are watts, but that just breaks down to being 1 joule per second. So whenever you think about power, always try to think of it in terms of joules per second. It turns out to be so important that we gave it its own special name, and we named it after a famous physicist whose surname was Watt. He was an inventor of steam engines. Now, something really useful comes from this. If you look at work as being force times distance, divide both sides by the time that you take, you can see that it becomes power is force times velocity, which is a really handy equation that we're going to use a little later. Now here's a test problem. We have a mass of 1 ton, and we're going to lift it using an electric motor. And we just go through a few ideas. Gravitational field strength is 9.8 newtons per kilogram, so weight is equal to m times g, as it always is. So that comes out, the weight of this object is 9,800 newtons pulling down, and we're asked to find the increase in the GPE of the mass when it is lifted. So if we lift it through a height of 20 meters in 3 seconds, let's bring up those definitions that we had a little earlier and see if we can use them. So the work done is energy transferred. Work done is force times distance. And we can use that because we know that the force in the wire pulling it up must be equal to the weight pulling it down, at least equal to the weight pulling it down, if not a bit more, in order to actually lift it upwards. So we know the upwards force on this mass is 9,800 newtons, and it goes through 20 meters. So multiply those numbers together, you get 196,000 joules. Now, if we want to know the power, that's just the rate at which that energy was transferred. So we're going to take 196,000 joules and divide it by 3 seconds, because that's how long it took to lift it, and that comes out to a power of 65,333 joules per second, otherwise known as watts. And finally, let's have a look at the efficiency. So if we're told that the motor has a power consumption of 100 kilowatts, we just found that it did 65,333 watts of useful work, but it's consuming 100,000 watts. So what's going on? We're losing some amount of power. And just by dividing those two, we can find that the efficiency is 65.3%. It's not 100% because we lose some energy due to the heat, electrical resistance in the motor, and friction in the motor's bearings as it's spinning. So not all of the energy goes into lifting the object. Efficiency, by the way, is just defined to be the useful power output divided by the total power input. You can also write it as the energy that you get out versus the energy you put in. They're entirely equivalent. Sometimes you'll be using power, sometimes you'll be using energy, depending on the problem you're trying to solve. And then we just turn it into a percentage by multiplying by 100. And finally, some handy equations. Commit these to memory. These are super useful. And as always, make sure you know the units for everything.